Today, it's our pleasure to have Dinesh Thakur from Rochester talking about Zeta and Multizeta for functional fields.
Thanks very much. I'm very glad to speak here because many of the story I'm going to tell about Zeta and Multizeta for function fields, many of the developments actually occurred here during my stay here. And more importantly, I would like to get a feedback from the experts here on the things I don't understand. So this is, as I said, in the function fields, and there are well-known analogies between global fields. So instead of rational numbers, we will be looking at rational functions over a finite field of characteristic P. Instead of integers, we will be looking at, there's a polynomial would be the analog. Then there is a usual absolute value is the absolute value coming from the degree here. That's the place at infinity, rational place at infinity I look at. The completion would be real numbers and there are complex numbers. So similarly, I usually denote this by K, this by A, and the completion by K infinity. So this looks like the Laurent series in 1 over T. So I'll call it K infinity. And big difference here is C infinity is the K infinity for completion. This degree being 2, this degree is infinite, and that plays a lot of important role in the subject. So another simple analogies are if you think of Z star, that's just units here are just A star, which is FQ star. So many times you will see the role of 2 or even numbers is played by Q minus 1 or multiples of Q minus 1. And other analogies, so another thing I will need is instead of Q being a sort of a canonical base, FQT, you have to choose a base. So sometimes I will also, I can take independent copy of K. So I will choose independent copy is like FQ theta, sort of independent variable. And in general, you have to keep the coefficient field and field of definition separate. You have to keep track of this. So I will sometimes need that. So I'll just say this. The next level of analogy is instead of you have integers give you nth power maps. So n goes to x to the n. The analog of that actually is the Drinfeld module, which is endomorphisms of additive groups over say F. And then you have say, so every A goes to something like rho A, X goes to rho A of X. So simplest thing I will start first with the Carlitz module, which is sends T to X goes to theta X plus X to the Q. That's called a Carlitz module of rank 1. And just like for this nth power map, you have exponential, e to the nz is e to the z to the n. We have exponential for Drinfeld modules, which is satisfies for every A in A.
Okay. A is some element of the ring, yes?
A is the element of the ring. Small a, right?
Ah, okay, so this is the...
A is like integers, FQT, right?
Yeah, and this is multiplicative in A? If you do this?
This is a homomorphism, ring of homomorphism, not multiply, it's a composition, right? In this case, endomorphisms are the like tau linear polynomials. So EAZ is CA e to the Z. So for example, E of TZ would be for this module, it would be just, if I put T is equal to theta, it will be TEZ plus EZ to the Q, or maybe I should put theta there, yeah.
There is E to the, there is a formal exponential, okay.
This is the usual exponential. This is the Drinfeld exponential.
So what is E of Z?
E of Z is some function. So I'm not say, okay, I'm sort of saying, just giving the analogy, right? There is, so just think about this.
Uniformization.
Exactly. There is a function which satisfies, there is an exponential function which will satisfy all these functional equations. And you can, for example, solve for it. Once I give you the equation, just like differential equation, you can just write down the power series for it.
E of TZ is equal to what?
Theta of EZ plus EZ to the Q. Okay, this is called Carlitz module. Theta is another variable, and that's the field of definition. So this is Drinfeld module defined over F. So T goes to theta, that's like the characteristic map. Okay, see, Z is, so to say, canonically everywhere. As I said before, you have to choose something in this game. So this is like the, this is the Drinfeld A module defined over F. Okay, and I'm to send T to theta on the tangent space. Anyway, this exponential has a lattice, kernel is a lattice here, 2 pi Z. Same thing happens here. There is a kernel is pi tilde A. just like 2 pi I is a complex number whose square is a real number, this will be a complex number here whose q minus first power will be there. Okay, so this is the period of what is called Karlitz module. So this would play an important role. And finally, you get roots of unity. Maybe didn't manage my board space too well. Yeah, okay, let me just. So I'm not going to explain these things more. Just think about that there are these functions like this. Okay. This comes from the theory of Drinfeld modules.
Okay.
Okay, and then just like your zeta n's, which are e to the 2 pi over n, we have lambda a's, which are this exponential pi tilde, 2 pi k over n, so I say pi tilde b over a. So there are two sorts of cyclotomic theories. One is a constant field cyclotomic theory, which is obtained by usual roots of unity. And this is the Drinfeld cyclotomic theory, which are the ramified sort of extensions, which are, maybe I can write down the Galois group, Q zeta n, this is Z mod n Z star. So very similarly, if I take K lambda A, this will be A mod A star. Okay. And this is, so the class field theory can be done explicitly, just like Kronecker-Weber theorem and so on. Again, I won't go in the details, but the class field theory is the rank 1 kind of theory here. And you can do any rank situation in these function fields. So the rank would basically mean, instead of this rank 1 lattice, you can have any rank lattice. And that has to do with this degree being anything. Classically, you can only have rank 1 and 2. Here you can have any rank. And you have some kind of arithmetic things. And the rank also corresponds to the degree in Q in here. There is a Drinfeld correspondence, sets up all those things nicely. And the whole point is this lattice is, was used by Drinfeld to do GLN Langlands conjectures, not only GLO and GL2, but he could sort of start doing GLN because you can have any such rank situation like that. So first I will just go. So we are not going to talk about Langlands direction, but first let me just go to zeta straight. So this exponential, because we are in a non-Archimedean situation, is a product formula. This exponential will look like exponential looks like so z times product of. So I call this lambda. Okay, just for short notation. So this becomes lambda belongs to lambda 1 minus z over lambda, because these are the zeros, right? So, and then this thing converges. So it's like a Weierstrass product, but you don't need a convergence factor. It automatically converges. This is the exact formula for that. The pi tilde is just a transcendental thing, just like that before. And this is easy because of this equation. If I normalize the first coefficient to be z, has a very nice simple, FQ k coefficients. So just like the Taylor series of usual exponential.
What is this equation? E of t z is equal to...
E z is a product of z, where this dash means lambda non-zero. Okay. Let me just draw.
Above E of t z is equal to...
E of t z, it's my handwriting. E of t z, it looks like theta e z plus e z to the q. Let me just put t is equal to theta here. So then, this is characteristic... generic characteristic situation. If you want, this is the equation. Okay, so you will get a Taylor series in. I should have put theta there or t.
But this formula you wrote down really satisfied that equation.
That's right. That's right, and that comes from the theory. Anyway, so I want to. So because of this formula, so what Karlitz did, like 40 years before Drinfeld, was he copied Euler's proof of zeta E1. Okay, so let me just show you. This is the one line. After you have this setup, it's just one line. You have this thing, and this is FQ linear because of that. This is FQ linear polynomial. So if I take a derivative, it's just the first term derivative, right? Because Q power derivatives are 0. So if I take a logarithmic derivative and multiply by z, you get 0 over ez. Okay. And that is by this formula, it's just summation z over lambda divided by 1 minus z over lambda. You develop this into geometric series, you get summation z over lambda to the n. where this is summation over Z and lambda. And lambda and over n. You have to, of course, throw away this 0 and so on. But lambda is nothing but pi tilde a. So this is nothing but summation zeta n over pi tilde to the n, z to the n. Because, and n only becomes q minus 1 divides n, because as you know, in a finite field, if you sum over powers of kth powers, you get 0 if it's not divisible by q minus 1, and you get minus 1, and maybe it is plus minus 1. Okay, so that's the proof that now these things, because EZ has an exponential, has a Taylor series coefficients k rational, these things are k rational whenever q minus 1 divides n.
Zeta n is the.
So what is a zeta n? Zeta n is what you should think of zeta n, that is summation 1 over a to the n, where a belongs to a, and I take monic. Just like you take positive integers for Riemann zeta function, I take monic polynomials. So monic polynomials, maybe I should have said that in the earlier thing, monic polynomials, so z plus is like a plus, which is the monic. If I do that, so this is, I will call it Carlet zeta value. So Carlet zeta value is now say that this is like 2 pi I to the n over Carlet zeta value is this rational number. And this is, if you look at this, this is actually generating function of Bernoulli numbers, z over e to the z minus 1. So it's just like z over e to the z minus 1 is Bernoulli number. This is, would be actually, and actually it is true that this is bn over z to the n over n factorial. And this is a rational function. This is a polynomial, but this polynomial has all the good divisibility properties. This rational number has good properties like Von-Stott theorem, Herbrand-Ribet theorem, and everything. So things work very well, and I'm not going to talk much about the details of this, but you get a proof that zeta n is pi tilde to the n here. And then so the question is the same thing. We have problems at, these are the even integers. So even integers, you saw that. So the conclusion, of course, here is zeta n over, this is the Euler's theorem, and Euler-Carnot's theorem belongs to K. And again, Euler's theorem is really the same. You use the sine function, product formula, cotangent, logarithmic derivative is the same kind of thing. So that's what he was trying to do. And then the next thing I want to say, so you can ask for the same thing. Now you can ask for what happens at the odd values. Okay, and the odd values you can do much more, but you need, instead of these Drinfeld models which are dimension 1, you need to go to higher dimensions. And this was done, so I am going to tell this story a little bit more, but basically I want to say that Greg Anderson had this notion of T motifs. So he went from, one thing he did was, instead of just additive group here, which are the FQ linear polynomials, you take powers of that. So you take G power of D, so that would be the dimension. The rank is the rank of the lattice here, the dimension is this. And so instead of, you have C mod lambda, or you can do C infinity, C to the D mod lambda, right? Of the other lattice is there, so that's what we are doing. G goes to GA to the D, and T motive mean you have some endomorphism like that. And then you can look at this thing to the GA, so this maps there. So you look at M of G, is the homomorphisms from G to GA. And that you think of it as a T motive, I will say why. And then you can also have this polynomials in Ft and tau acts like that. So you can make this as Ft and F tau module. So it's a left. This is the F. So this is GA over F. I mean, this, I have to have some definition field. The field of definition is this F, theta, and you get some Ft tau module. And there are some conditions.
What is the LOM?
Say that again. These are the sort of the projection maps. The coordinate maps, GA to the D to GA. Just this thing, the homomorphism from G to GA. I can just project on the coordinates, for example. I'm just saying that there is a T action by definition, and then there is a tau action, and you can get this thing as a T tau module with certain conditions. And these things are called T motifs. And the reason is there are no cycles or K theory or anything, but the T motifs for various reasons. First of all, these are just linear algebra objects. this linear algebra object, so you can show that they form a good Tannakian category. So there are also, you have to be careful with, these are not automatic, so there will be exponential map just from these equations which you get, but this exponential map may not be surjective. So exponentially surjective is a sort of what is called uniformizable. This is called, this has to do with rigid analytic triviality. So I'll just mention this word and I will say concretely in a second what this means. This is one of the theorem of, so you can talk about the periods by solving some equations. So that's what I want to sort of explicitly do that. So again, it's a sort of a whole subject you have to develop, but basically they form a Tannakian category.
So it was not clear just what is f of in the sequence J to J.
I'm just saying that once you have T as a map, then you have polynomials in T, right? F of T is just polynomials in T. These are polynomials in T and tau, right? I'm just saying that once you have, I should not have written, maybe this was enough, this probably was confusing. I am saying these things are left in G tau modules because you have action of T. Tau is a Frobenius in characteristic P. That is also gives you a ring of homomorphisms.
Tau is the Frobenius acting on JA.
Yeah. So I should, sorry about this. This is F tau.
So tau,
And this is a non-commutative ring.
and T is an endomorphism of G.
G, right. Okay. T is an endomorphism of G, and then I can think of this as a left FT tau module. This is a non-commutative ring. See, think about this. What happened here? Here, actually, this commutative ring sat in this non-commutative ring. Right? That's a Drinfeld module.
Right.
Okay. This is very similar to Krichever modules where, you have some rings sitting in the differential operator ring. So there are these kind of analogies which are going up, and Anderson sort of generalized to higher dimensions. And the important thing is it's Tannakian category. There are some conditions that T minus theta to the D kills the tangent space and so on. So the Tannakian category, so in particular, you can form C tensor N, where the C is this Drinfeld module. C is this Drinfeld module. So this particular Drinfeld module, that occurs like multiplicative group, right? Because it's torsion is the roots of unity. So now you are taking, that's like a Tate twist 1, and this is like Tate twist N. Okay. And this is how do you form a tensor product? That's very easy because you just have modules. You take a tensor product over FT and let tau act diagonally. That seems to be the correct generalization. So you can do everything explicitly. You get exponential. These things are nice. Exponentially surjective and real analytically trivial and everything.
So
and
uniformizable is stable by
say that again?
Uniformizable is stable by tensor product.
Yeah, you can show that uniformizable tensor product of uniformizable is uniformizable. Yeah. So so in particular, this you get that.
There is also a dual here.
Yeah. So and then what I want to say next is so these are the objects. So we came here, Anderson and I came here in 87, 89 for Drinfeld module special year arranged by Professor Dalin. And just before that, in 86, he had developed this. And your paper, who was not published on P1 minus fundamental group of P1 minus 3 points was not published, but both of us had read it and sort of read the preprint and saw that there is a connection with this and thought that there should be connection with zeta n to this. And then, so what I had done earlier in my thesis, part of the thesis, so in my thesis, I used like defined gamma functions, Gauss sums by mixing these theories and so on. But I also looked at some zeta values. And I had looked at in particular, I showed that certain zeta values are transcendental for r less than or equal to say q square or something like that. And even I had shown that zeta r over pi tilde to the r to the q minus 1 is irrational. So I had some results done by approximation methods. I just approximated these things very fast, but Roth's theorem fails in finite characteristic. So Roth's theorem fails in finite characteristic, and even the good, so I had approximated better than Roth, but it was not sufficient to give transcendental all the time. So there were some results like that. And also the approximation theory was not satisfying. We wanted better understanding as evaluation of this. So that's why then what we proved, so we joined with Anderson, what we proved is that zeta n is essentially, so again, I will just put under the rug the technicality is essentially the logarithm of algebraic point on C tensor n. Or in other words, this is the period of mixed motive trivial extension of C tensor n by trivial. So we give a period interpretation or logarithmic interpretation of this, and this point is a torsion point. So this algebraic point is torsion if and only if q minus 1 divides n. Okay. So now if you think of classical Lindemann-Weierstrass theory, you see Hermite-Lindemann theory, you see that logarithm of something, this would be transcendental. And so this implied, so this was done by, so the analog of Hermite-Lindemann theory was done by Jingyu, and the consequence of this was that zeta n is transcendental, and then for all n, then zeta n over pi tilde to the n is transcendental for all odd n, and zeta v of n is transcendental for all n. So this is Motivic, so these points worked not only at infinity but at all the finite primes. These zeta functions have interpolations, which you can do it by dropping things, dividing that like Kubota-Leopold kind of stuff. And you get all these strong results. And that was the case at that time. But then the transcendence theory got even better.
Of course, this is much better than what is known for the usual zeta function.
Yeah, actually, and I'm going to state even more, much better. So this is much better even then. But then the transcendent theory got more stronger. And there was something called Anderson-Brown-Papanicolaou criteria for linear independence.
Just a general question. You know, how much of this goes through if you were dealing with the ring of functions on some curve?
Say that again.
Suppose you replaced your
Yeah, I'm going to talk about that later. Let's just do FQT. I will be talking about higher genus. Okay.
But should I think everything that you've said so far has some analog for a higher genus curve remove a point, or?
Yeah. So basically, I can take there any function field.
Yeah.
Things are not completely proved in that case. Okay. So, for example, we have lots of examples like that. So these theorems, that's why I'm stating everything for FQT.
But before we get to transcendence, so this general story, for example, is rationality values.
This is very general.
That's very general.
That's very general.
I see.
This is very general. This C tensor n technology has not been developed in general.
Okay.
Let me just say that.
Yeah.
But there are transcendence results like that, which I had proved for a higher genus and so on. But it's not as complete as this. So let me just say FQT is already a big challenge here. Okay. So Anderson, Brown, Papanicolaou, so they said, so how are the periods come up? So here, once you have this module, there is you can use T basis. So the dimension is, the rank is like the tau rank, and the dimension is the tau rank, and rank is the T rank. So the way the periods come up in this story here, if you have a motive like that, why is it a motive, by the way? Not only that this is a nice category, but there are cohomology realization. There is a Betti realization, Ita realization, Diram realization, crystalline realization. There are all kinds of maps and comparison, isomorphisms and so on. So it is a good reason why it's a motive. I'm not explaining that. But it's a good notion of motives.
How can you have a Betti realization if you haven't characteristic T?
There is one. It's the lattice kind of thing. It's an analog of those things. Okay.
Okay.
These are not the usual motives. These are T motives. These are analogs of that, and all kinds of realization and comparison maps over. On the other hand, that thing is not necessary for what story I'm telling. So I'm here a whole day tomorrow, and I will be glad to give more details on those things. But Anderson, Brown, Papanicolaou thing says, so if you have an n tau action, so you have matrix, which is giving you the tau action in this module situation, you solve some kind of Frobenius difference equation. And then the point is the period matrix of this motive, the way Dinesh, cohomology and everything works out, the period matrix is nothing but this C evaluated at T is equal to theta. So remember, this tau action has theta coming from t coming from here and theta coming from the coefficients here. So these are like two variable things. In general, we are looking at a function. You are looking, have a curve, any curve. You have product of curve with itself or curves with itself, and we are making algebraic functions on that. That is the crux of the matter. We make algebraic functions on products of curves, which have the property that when I restrict them to the dth power of Frobenius, they give you the dth term of something interesting, like the gamma product or zeta sum, according where d is the degree. Okay, so this is the key point. The key point is constructing algebraic functions which give you this module of on curve cross itself, so that the periods you can compute, because this once you get this motive, this period computation is there, and this thing is, this says that the period, linear period k bar linear period relations between periods, sorry, k bar linear relations between periods. That means after you substitute t is equal to theta between periods, come from Motivic relation. What does that mean? Come from Motivic relations. That means two variable relations. So without, ft relations, these are ft, f theta relations. These are theta, you are thinking of f as your numbers and t as a, so to say, function. So there is an extra variable there put in there. And I'm saying that the relations between the numbers are coming from relations between the functions at a higher level, which form the motive. This is what this Anderson-Baranoul-Papanicolaou criteria says. And if you are familiar with the classical theory, this was done after 2 years after that. Boykers proved an analog of Ziegler-Shidlowsky theorem. So maybe some of you have seen that. So I'll just say that Boykers 2006, this was 2004. And earlier, so what he is the Ziegler-Shidlowsky kind of thing for E functions. So the relations between the values of the E functions come from the E functions with lots of hypotheses. Okay, this is exactly the same kind of theorem, except now it is giving you very strong implications because of all this machinery. They are giving you the relations between periods. This theorem just doesn't have that applications. Okay, but the strength of this thing is the same. E function, so the relations between the values come from the relations between the functions is the same thing here. And in particular, because this is a period, you get a Grothendieck, and you have the Tanakian formalism. So algebraic relations are basically relations between the linear relations between monomials. Once you have tensor product, you can do monomials. So I'm just saying philosophy, I'm not really proving things, but you can just prove Grothendieck's conjecture for this thing. So in other words, in general, so the period conjecture as the period relations come from Motivic relations. Okay, period relations come from Motivic relations. Period relations come from Motivic relations. And so you said this was a strong, so now Chang and you use this. And so the same input as Motivic input as we have, but now stronger transcendence theory, and you get that all algebraic relations between all zeta values come from that one, Euler-Karlitz relation. And there is one more in characteristic P, zeta n to the P. All algebraic relations come from this.
Sorry.
So
what is n?
n is any positive integer.
It has to be divisible by q minus.
No, this is the q minus 1 relation, right? And this is, so all odd ends also. So I'm saying that not only that, you understand all algebraic relations between all zeta values, even or odd completely. Okay, so because of this transcendence theory, and now, so I took, this was supposed to be my 10 minutes. Now it's, so then if you, why was Euler studying multi-zeta? Euler was studying multi-zeta because he thought that he only half succeeded in solving the problem. He thought that he got the even ones, So zeta even and zeta odd, you didn't see that. Then he looked at multi-zeta, and he did get some interesting relations like zeta 2, 1 is zeta 3, the odd one. And he thought that eventually he might succeed, but then probably, I mean, in some sense, he didn't succeed. So in some sense, that problem is done here. But still, multi-zeta is interesting. And that was, I realized that when I was here again in 2001, and I attended Professor Dalin's course on multi-zeta values and realized the rich connections this subject has with lots of interesting structures in mathematics. So I started developing multi-zeta. So what is a multi-zeta here? Usual multi-zeta is like 1 over n1 to the s1, nk nr to the sr, where n1 greater than nr greater than 0. So there is no order on polynomials, right? There is no order, but there is a partial order given by degree. So you replace, so I define multi-zeta values. By replacing this positivity, you mean monic. So you say an AI monic. And these things, instead of that, you get degree of A1 greater than degree of AR, and then you make A1 to the S1, AR to the SR, where AIs are now polynomials. Okay, so this thing, if it's in the depth 1, this thing is in depth 1, you do it in higher depth. As soon as you do that, you see a problem, because once you have that, you have zeta A plus A times zeta B is zeta A plus B in here. So I mean, here you have zeta A plus beta plus zeta AB plus zeta BA. And that is because when you multiply two of them, if say with N1 and N2, either N1 is equal to N2, N1 is greater than N2, or N2 is greater than N1. But we don't have order, so this fails. And it took a long time for me to understand. So even though I was doing partial, it was not clear that the product, and this is a great identity because product of zetas, and then you can do the same thing for multi-zeta. Product of zetas is sum of zetas. What that means is algebraic relations study reduces to linear relations, right? And classically, of course, there is another relation comes from integral shuffle relations, and the double shuffle relations are supposed to be the whole story. But anyway, let's start to look at this once. So it was not clear, and see, these things are, so this thing a priori is in K infinity. It's not even clear that this is non-zero, right? So I had to, this is a hard theorem to show that this is non-zero. So this is a non-zero, so you look at the power sums, and so if you look at the power sums, I use SDK, it's suppose summation 1 over A to the K, degree A is D, and monic. These degrees are erratic a little bit. For FPT, they are better understood. FQT, there are still open conjectures about how these things are. Some conjectures, some theorems here imply, so to say, Riemann hypothesis for Gauss zeta function interpolated from that, but that's totally different story. So I just wanted to say that this kind of issues come up even in non-vanishing. And non-vanishing is the first step of transcendence, right? So I proved that these things are non-zero. And this was actually used in the sort of transcendence proofs later on. And then Anderson and I, again, what we showed, so actually I'm jumping a little bit in the chronological order, but what we showed, so with Anderson, what I could show that is these values are periods of iterated extensions of C tensor SI. So just like mixed state motive story. Okay. So this is a theorem. Now, as I said, it is not clear that this thing fails, this doesn't work. But I conjectured lots of relations between these, like product being sum, and I could not prove the conjectures. So finally, I bypassed the conjectures and showed that it always exists. So the product of multizetas is always, so the theorem is product of multizetas. So these are what are called MZVs. Product of MZVs is sum of MZVs. So again, algebraic relations reduced to the linear relation study. But now I want to give you one example, the formula. So I gave it, and then this is universal. For any curve, it works. So these relations, so let me just write down the formula, and then I will say zeta A, zeta B, minus, I will write this, zeta A plus B, zeta A B plus zeta BA. And I'll write this equals summation minus 1 to the A minus 1, J minus 1, A minus 1, plus minus 1 to B minus 1. And I will have two comments here, Q minus 1 divides J. So this depends for multi-zeta, this maybe FQ tier as you suggested, you can go in any curve. I always use rational point at infinity. That makes use of signs easier. Okay, so rational point at infinity, these are universal relations. For any A, you make this definition, any genus A, you will get the same relation. It just depends on Q. And it's curious, there are two things. First of all, the coefficients are in the prime field. Prime field in characteristic 0 is rational numbers. Prime field in characteristic P is not rational functions, it's FP. So these are in our FP, plus this looks like sum shuffle. If you remember your formulas for integral shuffle, this looks like integral shuffle actually, except for this condition. So this kind of things comes up in a depth 2 integral shuffle. Okay.
Wait, what is that?
Zeta A plus B minus J. Okay, so weight has to be A plus B. These things preserve weight. So once you have this thing in motives, Chang showed that relations preserve weight and all MZVs are transcendental. Relations preserve weight. All are transcendental. All MZVs, as I said, non-zero, and then we can prove they are transcendental. So we have very strong results again for multi-zeta values here. But two comments again, as I said. One, that this is in the prime field. Why did it take a long time for us to see that? Because this thing's in FP. So many times this is 0. In the whole point is in characteristic 0, you add positive things, you don't get positive things. Here things are cancelled. So sometimes when we are computing, and I compute very slow, you get 1 or 2 terms, sometimes you get 10 terms. And it depends on Q. So for each Q, there is a different formula. So finally, similar techniques sort of used at the end, and you got a nice formula, but this has some interesting story here. So then, okay, since I'm not doing very well on my time management, I will sort of jump a little bit on here.
Sorry, so after the fact, is there an elementary proof of this? Like, could I just manipulate and find?
This thing has elementary proof eventually. What I'm saying is the story was complicated. This thing has an elementary proof, absolutely. This thing is an elementary proof. The first, so first I had proved, so okay, I should say that first I conjectured, and when I realized there is a formula, I proved a formula without proving it. I just said there is a formula. Motivic philosophy did help me because I realized that this kind of formula should work at the level of motives. That means it should come from the identities of these two variable functions, which means that it should come from identities over degree D things, and that actually worked here. Okay, so Motivic philosophy does help, even though there is a completely elementary proof at the end. Okay, so one thing I wanted to say, maybe I will, Okay, so I think I'm going to skip this thing. So this is, we also proved, Anderson and I also proved analog of Ihara power series. Ihara power series. And what does, I will not write down anything. I will just say that, okay, maybe I will write down one thing. You have an absolute Galois group of K, and you have A, and you can complete it at any prime, finite prime, and you make a power series over that. We get a cocycle, one cocycle I sigma, which is sort of trivial over the cyclotomic field. And so you get a big representation, meta-abelian representation. This power series I sigma, this is called a Ihara power series. It interpolates all Gauss-Jacobi sums over a V-adic tower, and its coefficient contains information of Deligne-Soulet cocycle, which you can say it in two different ways. These Deligne-Soulet cocycles can be described in terms of units, cyclotomic unit, higher cyclotomic units, if you know the classical theory, and also these extensions which I mentioned, which give the zeta n, those extensions correspond to the Deligne-Soulet cocycles. So even though we don't have the K theory understanding of the Deligne-Soulet cocycles, the cyclotomic understanding and zeta understanding still works here.
So what
The coefficients.
What you're calling the lean Sulikos has some explicit realization of Galois cohomology with coefficients in a Tate twist.
Right. Yeah. Right. So and this is one variable. Ihara originally had a 2 variable, and then Anderson, that's like a beta functions using the Fermat motifs. So that's like we do the analog of that. And here we factor it into gamma things. Anderson had to go to hyperadelic situation. Here you don't have to. So there is a technical advantage in a function field. At the p-adic level itself, you can do it. You can't do that in classical case. So there is some technical advantage here also. We did not pursue. So this thing is harder on Iwasawa theoretical thing because this is like infinitely many copies of ZP. So ZP, Iwasawa theory techniques have not been developed yet. So we could not make lots of uses of it yet. But there is a, and so what I wanted to say is, this multi-zeta values come up in the fundamental group of P1 minus 3-point studies because they are also given by iterated integrals of dz over z and dz1 minus z, which are the holomorphic forms on this. And so through the chains theorem. And we have no idea what the corresponding object here is in function field is. Even the Bayes' theorem fails, right? Bayes' theorem, if you think about it, Bayes' theorem works over prime field. So you get, I mean, if you have, even a affine line has lots of covers. So if you have, so Bayes' theorem actually, instead of P1 minus 3 points, you can map curve over P1 minus 1 point, if you allow wild ramification. If you want to make tame ramification 3 points, still either you get FP and you already know it's Galois group, or you don't get to the function field. So, but instead of, so Grothendieck, so there are 2 programs of understanding, trying to understand absolute Galois groups. One is the Langland's conjectures and one is Grothendieck program. And the funny thing is, if you start with these objects Drinfeld created to do Langland's conjectures and generalize these things, we somehow end up with the pro-unipotent version where Professor Dalin showed how to put good mixed motive structure. So we don't have the original object, but somehow we have the next category of the pro-unipotent thing. And this is the Dirac-Betti story. And this is the Ital theory.
Of this conjecture, at least in for classical multi-zeta about the dimension of the space.
That's the next thing. Okay, that's the next thing coming. Okay, so now that's what I'm going to say next. So what are the linear relations now? So that's the question. What are the linear relations? So my student, so I had some more relations. These relations were in FP, but I proved one more relation, which I will write down. Only one relation I'm going to write. I proved several relations. One relation which is interesting is zeta q divided by t to the q minus t. Okay. So this is like, I would say zeta 2, 1 is like zeta 3 kind of relation. So I called it Euler type relation just for thing. And then my student Josh Todd, in his thesis, what he did is like what Zagier did. So dimension formula, you want to understand the dimensions of a given weight because these relations preserve the weight. You want to understand what are the dimensions of the multi-zeta values, span of the multi-zeta values of the given weight. And I had conjectured that there are no relations in weight less than or equal to q minus 1. And this is the first relation of weight q, right? And then the question is what happens next? So he did a lot of numerical studies, just like Zagier did using Parry. He had to develop his own LLL algorithm in function field, and he has to do it for several qs. There is only one rational number field. There are lots of rational function fields. So he had to do it for several qs, and he noticed that dk is dk minus 1. So that is Todd recursion relation. He conjectured this, dk minus q. And so I will just write what Zagier had. Zagier had dk, so k is the weight. Weight k span dimension. Dimension of weight k span is dk. Then Zagier had dk is dk minus 2 plus dk minus 3.
When you speak of dimension, it's over
q.
field.
Over q or q bar. And I'm using it over fqt, function field. Function field. Okay. Another conjecture I have is that they are all linearly independent over fp. That conjecture is still open. I will say something about that. So this is a George his conjecture that this is the recursion instead of that. It depends on Q. And then so his conjecture is now proved. Okay. And
so it specifies that the dimension over FQT, but and also over the algebraic closure.
yeah, this is dimension over K or K bar because of the transcendence theory. Right.
So
But not over FP. FP, these things are different.
and the fact that dimension over K and K bar are the same is non-trivial.
It's not trivial. It's a transcendence theory fact. It's like Baker's theorem. Baker's theorem, you have linear forms in logarithm, or if Q bar relations are over Q relations. It's that kind of transcendence theory. Okay, so this is what you get. And Juan Godak. And then I conjectured a basis. So I conjectured a basis for this. Basis is zeta S1 to SR, where SI less than or equal to Q, and SR last one is less than Q. And this you can compare with Hoffman conjecture, which said that the basis SI is equal to 2 or 3. Okay, so this thing matches with that recursion, and it fits with what I had. So that was my conjecture. And Tuan Godak 2 years ago showed that this basis I conjecture actually spans this space. Okay, there is like Brown's theorem, for example, but it's much easier. So actually we had identified, so when he did a lot of numerical analysis, and the idea I had was you have shuffles. So these multi-zeta values are iterated. So that means they look like at the degree D level, you have something like this, SK, S less than D. So this is like the iteration. Less than D means you sum up to from degree from 1 to less D minus 1. And you have, these things are sum of such kind of things. And you can multiply with SD here or S less than D there and use this shuffle.
What is SD?
SD is the power sum, which I wrote down here. It's except I'm using multivariables. Okay, so S for sum, power sum, D is the degree, and these are the exponents. Okay.
Could you read the conjectural base? I cannot.
The conjectural basis is zeta S1 to SR, where all SIs are less than or equal to Q, and SR, the last one is less than Q. Last one is less than.
No. So SD of S is the sum of powers. Like before, but for several one you take.
That's right.
That's
right. You should do it like multi-zeta.
With degrees decreasing, starting at D.
Yeah, at degree D. This means degree D is the starting thing and the lower things, And so I'm just saying that, by pre-multiplying and post-multiplying and using shuffle relations, idea was to get all relations starting from seed relations like that. And Todd realized that I thought I would need more. He realized that this is the only one remaining. So he had another conjecture that these two processes of shuffle with this give you all relations. And this is all has been proved. So now it's a funny story. So he proved first that, John Doc showed that these things span the space, span the weight spaces. And then you have to prove linear independence. So that's the transcendence theory. And there are two groups. On one day, like 1.5 years ago, I got email from him, and he sent me a paper by In, Kim, Lei, Godak, Fan. And the same day, I got another email from Chang, Chen, Mishiba, both claiming to prove both the conjectures. So, of course, both used each other's earlier works. Okay. So Chang had done, that work and using multipoly logarithm and so on. So we give these things, we give Motivic interpretation. This is very explicit. So you can write things in terms of multipoly logarithms and so on. So that was used. This ABP kind of transcendence machinery was used to prove linear independence. So they used his spanning result. He uses their transcendence results, and both proved what the conjectures are now done. Okay. One more thing, so both these conjectures are now known. One more thing here is this kind of thing generalizes to higher depth multi-zeta. So multi-zeta times multi-zeta is also like that. So you can make like Hopf algebra with product coming from this and some co-product. And my student Shuhei Shi. So again, because of time, I'm going to just say it. With anybody interested, I can show you exact formulas. My student Shuhei Shi, we had an Hopf algebra by making and it mapped to the multi-zeta values. It's an algebra homomorphism, and we also got a co-product. So Hopf algebra means, just like this theorem means that multi-zeta have Motivic lifting, this theorem means, so there is a Hopf algebra, which algebra mapped to MZVs. This means that multi-zeta values are like algebraic functions are some functions on the algebraic group, right? So some pro-algebraic group is there in the structure such that these things have lifting there. Okay, so this is a rough thing. When I say she proved that this is a Hopf algebra, we guess some relations of product and co-product, product coming from here and a co-product and antipode and everything. And we could not prove associativity and co-associativity at that time. Okay, so that was conjectural. We just checked it on computers, hundreds of things, and it seems to work. Okay, so this was a conjectural Hopf algebra, maybe I should say, conjectural Hopf algebra, which lifted the multi-zeta values on algebraic groups. And this conjecture also has been proved now in a 100-page paper by this same group. It's so I have not read the complete proof, but okay, two things. I knew it's associative if the multi-zeta values are linearly independent of FP. That just follows from associativity here. And so that was my conjecture. That is still open. Even though this conjecture is done, we don't know whether the multi-zeta values are actually related or FP. And I assume they are not. So that would imply associativity. Now associativity is proved, but that conjecture is still open. So we still don't know independence, but associativity is done, co-associativity is done, and it was done by this group. And I want to again say this especially here because Professor Dalin had sent me a letter about how to approach this, and I did not do that, but I sent it to them, and they told me that that was useful. So thanks. Okay, so this was this is the Hopf algebra story, and now
It's commutative Hopf algebra.
It's a commutative, yeah, commutative, not co-commutative.
And what kind of group do you get?
I mean, still, there is a lot of work still going on there. We have to sort of work this out. There are, okay, one more thing, cyclotomic multi-zeta values. So Dalin and Gonchara had a paper where instead of just P1 minus 0, 1 infinity, you throw away the n roots of unity, and what you get a colored multi-zeta or cyclotomic multi-zeta. So many years ago, I had conjectured two types of cyclotomic multi-zeta, depending on two cyclotomic theories which I talked about. One looked like product of zeta I to the, so you have AI to the S, Si, and then zeta, AI to the DI, let me just say, where this DI is the degree, so let me say degree AI. Or you can have sums of product of CAI lambda I over AI to the SI. So that would correspond to the constant field degree cyclotomic extension. This would correspond to the Drinfeld type of cyclotomic extension. This would be, so you make similar iterated sums ordered by degree, and either you use the Carlitz torsion or you use the torsion roots of unity. Okay. So these ones, there is again the same guys, they have proved, so these dimensions are understood. Dimensions are understood and dimension basis is understood. And actually it turns out are understood. So I should say that I had proposed these two things. This one was developed by Harada and Yo at UPenn, and this is in Japan. And these people, they show that the basis here, so I should give you the basis. I think I erased that. The basis conjecture is gone. The basis conjecture, there is another basis which just is as simple as Q does not divide SI. There is another basis Q does not divide SI, all SI, zeta S1 to SK, SR also is a basis. For the usual multi-zeta V's in function fields, and if you use the cyclotomic ones, the same condition and these things just don't matter. So in other words, the cyclotomic ones are very simple. There is not much interaction between the constants and the functions, and the cyclotomic ones are much simpler in contrast to the case you studied where the n really mattered. But I think that complexity will come up through these ones because those cyclotomic extensions are harder. These are constant field extensions. So somehow the cyclotomic extensions here, you are not getting much richer theory. You are getting, basically it reduces to the usual multi-zeta values. If these roots are FQ rational, then that's like alternating or Euler sums. If they are higher roots, you get something interesting, but the relations don't show anything more interesting. But this theory, I believe, is going to give you more. So I'm interested in.
You again have products.
Say that again?
Are products linear combinations again?
Yeah. And by the point is by the same formula. They don't have to work harder. You just put some roots there, roots of infinity, because constants don't interact with the other terms. So it's very easy.
And do you have a Hopf algebra again?
I'm not even thinking, but I'm sure these guys will develop it. Yeah, I'm pretty sure there will be Hopf algebra. But what I'm saying is the theory doesn't look like much richer as in the case, because in classically the constants, there are no constants in Q, right? And that's why things are, interaction is making things complicated. That should happen here. That should happen here, not here. That's my just a guess. And again, I'm saying it, I'm sticking my neck out just so that I will get some feedback. So I want to say a few more things about, let me just say these.
I didn't understand the statement. So you are looking at this cyclotomic generalization, and you say that what is the QS also is the basis? What is it?
Yeah, so I'm saying that I gave one basis, right, which was that all SIs are less than or equal to Q, and the last one is less than Q.
Yes.
Instead of that, you can consider another basis where the only condition is none of the SIs is less divisible by Q. But SIs can be big now. So my basis had an advantage that SIs were bounded. Now they are not bounded. But I think this is important. So now let me now say.
Basis for what?
Basis for the space W. So you fix a weight. What is the weight of multi-zeta value? It's the sum of SIs. You fix the weight of the multi-zeta. You look at all multi-zeta linear span of all multi-zeta values of that, and that's what you're spanning. It's the basis of that vector space over K or K bar. So what I want to say here is the following. So classically, mixed state motives, so what, I don't know, MTQ category, you have the group, which there is a unipotent part and there is a central GM. And this MZV is, so to say, span, this corresponds to the MZV with the Brown's results or something like that. And the dimension series, summation of this decay T to the K is like 1 over 1 minus T square minus T cube. And because of there is a central element of dimension 2, you look at something like 1 minus T square over 1 minus T square minus T cube. And what you get is basically you see that this thing has Lie algebra where there is a one generator in each odd degree, one generator in each odd degree. If you try to do the same thing, our power series is 1 minus T to the Q over 1 minus T to the Q. That's the dimension series coming from the Todd's recursion. If I divide by that and develop that in the geometric series, what you get is like one generator in each degree, not divisible by Q. You would say Q minus 1, it's Q though. You would think by analogies that 2 will be replaced by Q minus 1, but somehow Q is there. To do that, I have to forget about this central thing. And we talked about, I want to understand this still better. In non-Archimedean situation, this thing kind of goes away. So it's possible it's there. But this it's not a V-adic situation here. It's an infinity-adic situation where, so this thing, so for the dimensions result, I had guessed this, but then I was always using this, and then the generator and relations were getting complicated. The point now is that if you do that, that seems coming up naturally in all these things. So there should be a group whose Lie algebra will have this kind of situation, and it has to play some role. Now I exactly don't know how it is. The main problem is we still don't know whether this is true, and right now it doesn't look like that. The reason is, if you look at the extension of extension C0Cn, trivial and C tensor n, which I was using the notation. If you do it in notion of T motives, Anderson T motives, it's extensions of the motives, trivial motive and C tensor n. Okay, it's like Z0 by Zn. That's what I'm looking at. So this is dimension 1 or 0, depending on whether n is parity of n. In function field case, this is actually not. So if you use the T motives, these things are not even finitely generated. The reason is it's like mixed Hopf structures. It's not a full T motives for this respect. Okay, so it's the T motives is great for many other respect. If you use Stukas, compactified Stukas, these are finitely generated. So Laforgue and Talmont developed that, and they got something finitely generated, but still there was a problem because it was not Cn invariant. So they had some restrictions put in at infinity to make it finitely generated, but they didn't get right descriptions. You have to have these extensions which are exact on the Hodge level. So you take the Hodge realization, and they were not exact the way they were defined. So it's so this is, I have not read all the papers, but this is oral communication from Gazda and Morris chair. They seems to have now extensions which have this correct property, but the dimension comes up to be n if it's even, and n minus 1 if it's odd. So there are two things. Instead of 0 and 1, you are getting this dimension. So either you put more restrictions and get MZVs, or these categories are MZVs is just like a sub thing here, which corresponds to something else, and this is a bigger thing. There are two possibilities, and it would be great to understand what is the correspondence between the mixed state motives, because with the iterated extensions and so on. But at least now we have good candidates to compute with these things. And but the analogies just doesn't work. So things are better in a sense that few years ago it was not finally generated, it was finally generated, but still not good. Now it is good, but still bigger dimension than you would expect for a even stronger connection. Okay, so that's one thing I wanted to say. And I have already ran out of time, and so let me just take 2 minutes if you don't mind. And so yeah, there was a V-adic story, finite adelic story I have still not even touched. So I will just say one more thing. You asked about higher genus things. So higher genus thing, I had something called so I defined something called Zeta-like and Eulerian. I've defined two things, and what that means is multi-zeta value zeta S1 SK is zeta-like if the ratio with the same weight, just the single zeta, is algebraic or rational. Algebraic or rational is the same, again for the same reason. If zeta divided by the zeta, multi-zeta divided by zeta is rational, I think of this multi-zeta as a zeta-like. And if it's the weight is even, I call it Eulerian, because then it would be pi raised to weight, 2 pi raised to weight times the algebraic thing. So I had conjectures about what these things are, and I will end with a couple of just two things. So there was classically, I looked at the classical thing, there was no conjecture, but I looked at the data and talked with people, and it looks like zeta 2, 1 to the 2n plus 1 seems to be the whole family of order weight zeta. Order weight zeta-like. Those are the only things known. In function field case, I have more properties. And here is the conjecture my student Lara Rodriguez and myself we made. Conjecture is if zeta S1 to SKR is zeta-like, then That's the definition. Then zeta S2 to Sk is Eulerian. And if I drop from the other end, zeta S1 to Sk minus 1 is zeta-like. So this conjecture, this one is proved and this one is not proved. See, the reason I state this is, this again gives you some kind of structural, interesting structural understanding of these conditions, which has to be understood better in terms of motives. So you can use the motives and the explicit realizations to do that part, but not this one.
What is Eulerian?
Eulerian means it's the same zeta-like of weight E1 is called Eulerian. See, Eulerian, because of what is Euler? Euler's theorem says that E1 weight, this thing is a pi power times rational, right? So if it's Eulerian, that means the weight is E1 and zeta S1 to Sk is pi power times algebraic. So it's like simpler, right? Than the zeta. This is like a zeta odd or E1. So I'm saying that this kind of conjecture, this is proved by Chang, Yu, Papanicolaou.
What we don't vector this.
I'm saying that suppose if this is zeta-like, then I dropped first term, this is Eulerian. Then I can drop this one, I can drop this one. So all of our Eulerian.
So that's an implication.
That's an implication. The conjecture is an implication. Okay. And another implication, if this is zeta-like, then if I drop from this end, they're still zeta-like. And this is, we just don't understand is in terms of motives right now. This is understood. Now, finally, the higher genus case, higher genus, we proved some zeta-like and Eulerian things. And this is the one thing I wanted to say. So far, the zeta relations were motivic relations in a sense that they worked in the level of these algebraic functions on the product of curves. We proved this in a higher genus, but when you try to match the functions, they don't match. But when you so the way we prove it, when you subtract these functions, the error, which depends, I mean, these functions are functions which have sort of d in the parameter degree. And when the degree tends to infinity, the error goes to 0. So it's a rational function, has a negative degree always. So there is a big difference in the genus 0 and higher genus 0 case. When you try to prove these relations, we use the motivic techniques and we can get a proof, but we don't see in what sense they are motivic, in a sense that instead of working straight at the motivic level matching, there seems to be something, the difference is of negative degree. So when you take limits, so there is some analytic process, then it goes to 0. So this is something I would love to understand. And I think I'm sorry about going over time. There is also a V-adic story here. You can, because this is motivic, you can interpolate this as a V-adic things. And just like you had done and Furushua had done, there is a V-adic motivic multi-zeta functions. And there are V-adic interpolated zeta functions. In depth 1, both are same. In higher depth, they are different. I had done interpolated one.
What's depth?
Depth is the depth of the multi-zeta R.
How many?
How many SIs? That's the depth. And the weight is the sum. Sorry, I just assumed that everybody knows, but the depth is the number of things and weight is the sum of SIs. That's the standard terminology here. And so my another student, Kibin Shen, his thesis, we looked at relations between the interpolated ones and the V-adic ones. There is also finite adelic analog of multi-zeta values, which is made by looking at the sums where you choose a prime and you spend degree P less than D1, less than degree A1 and so on. And you look at 1 over A1 to the S1 and so on, and you look at it mod P. So that's just a finite sum. But the whole point is you look at the relations which work for almost all P, all for except finitely many P. So you take a product over P divided by this direct sum over P. And this kind of thing, classically, the weight spaces of these things and the V-adic things are the same. And in our case, they are different. This is another interest. So that means there is something different going on in terms of motives here, that the weight spaces are different. And on the some subspaces, we are getting connections. So the V-adic ones and V-adic interpolated ones connect on some subspace. These ones and the other ones connect on subspace. And we have conjectures on various weight spaces. And I will stop here. Sorry to have gone fast, but I will be here whole day tomorrow and today. So please ask me anything and I can give as many details as you want.
Any questions for speakers?
Why in your conjecture, you sometimes drop the last variable and sometimes the first one? Like, I thought this was so much.
Say that again?
Why in the conjecture,
In
sometimes,
this thing.
sometimes you drop zeta one, S1, sometimes you drop SK.
Yeah. So, I mean, you can, I call this slicing from this side or that side. That's if this side I slice, I get Eulerian. This side I slice, I got Zeta-like still. This is a conjecture. We still don't know why. We know this why. In terms of motives, there is an explanation of this. This is proved. This we don't know. This is, and we have also splicing conjectures. So we have a complete conjectures about what the Eulerian thing should be. Classically, I have not seen, but I have this guess, and I asked Broadhurst and other people, and they say that it seems to fit with what the data they have. But we have some more families of zeta-like in for FQT. For higher genus, they seem to go away.
Okay. Excuse me, in the conjectural dimensions, you said that the dimension over the function field in algebraic closure should be the same.
Yes.
And now you take the definition of zeta-like, you write that the quotient is in K bar. But
RK.
Then it should be K actually.
Yeah. Do you want that?
Well, okay, it's the same.
It's the same.
Okay.
It's the same. So I mean, one way is to a priori stronger, right? So yeah, it's supposed to be the same. Yeah.
You said that there were some shuffling symmetries though, or no?
Say that again? So double shuffle. One more thing. Classically, there is this philosophy of Ekal, which I never understood, that there should be double shuffle for all these things, right? Now, if you think that there should be double shuffle in this case, the integral shuffle preserves depth. Here we can prove that it won't, if there is a double shuffle at all, it won't preserve the depth. Why? Because in the lower weights, there is no double shuffle.
What is double shuffle?
So classically, there is something called sum shuffle, which occurs by shuffling the order of the AIs, NIs. I wrote that somewhere, A plus B, AB and zeta BA. That's called sum shuffle. And similarly, you have iterated integrals and you have differential forms. And the way the iterated integral works, you can shuffle those forms. And there is still some relation. That's called integral shuffle relations. And classically, the theory, conjecture of Zagier and several people is that all the relations, linear relations between multi-zeta, are putting this shuffle equals to that shuffle. And you have to do it for some kind of regularized values because there are some non-convergence issues which don't occur here. We have everything convergent.
So for the usual thing, the conjecture is that the relation coming from series multiplication and integral multiplication are enough for all the relations.
Exactly.
And Brown's work proves that the Motivic, okay, so it is not clear that they generate even the Motivic relations, or is it?
I had to think slowly. Maybe you can answer very quickly. I had to sort of sparse it. I had to think, generator. I mean, there are inequality this direction and that direction, and sometimes I get mixed up if I don't speak it up.
The key talk of Delin on Brown's work 10 years ago, or more than 10 years ago.
So you get an upper bound in that case, right? I mean,
if you work with the Vygotsky's motives, you get enough relations to get the right dimension.
Right.
But the question is whether
those are independent.
The naive classical relations are enough already for those. I'm not sure. I'm not.
We can talk later. So just one more thing here I wanted to say is I can show that, for example, this adelic ones, if Q is equal to 2, adelic ones 1 is not equal to 0, interpolated ones is non-zero. But if you think about Q is equal to 2, so then this is a weight 2 space and zeta V Motivic 1 is 0. So this is the simplest example where I can show that the spaces are different. Classically, this doesn't happen. So this is something.
U equal to
2, and this thing, see, I'm sorry, because if you have not seen some of these, I have not given you complete definitions. I am saying that you are looking at the finite variance. These were done by Hoffman. And then you look at things, relations which work for almost all P, for all large P. Okay, classically, and in this case also, large means large degree. And if you look at that, I show that this thing doesn't work for all large primes. Interpolated one is not zero, but the Motivic one is zero, so their spaces are different. Even the spaces are different, and zeta V2 is also zero. So weight 2 spaces are different, and there are this kind of differences coming up.
What do you mean zeta V Motivic one?
So Motivic, you can think of it as coming from crystalline cohomology. Okay, so these things come from DRAM and Petit cohomology, right? The periods, usual zeta values are shown up as the usual periods. So you can either use multi-polylogarithms and do interpolations and do it. See, these ones I defined by just interpolated like classically. I just interpolated the power sums and made these functions. So those are periodically continuous functions.
Yes.
The multi-zeta values, Motivic multi-zeta values are not periodic continuous functions. They are values. They are periodic values. They are not continuous functions. These are continuous functions.
But is it possible?
Of what? Of
the periodic variable.
Okay.
Okay, these are the values that only at integers. You can't interpolate. These things you can interpolate. So there is plus minus points there, but these satisfy exactly the same relations as the classical one, and it satisfies that zeta v of q minus 1 is multiples of q minus 1 is 0. That comes from the trivial zeros of Riemann zeta function. Okay, and this same result is true for our zeta function also. So that part works exactly the same. So the weight space, if you look at the weight here, dw would be wp would be dw minus q minus 1. Because that is the relation coming from multiples of q minus 1. So that's the way this works here. This doesn't work here. There is a different conjecture for dimensions here, and in usual mixed state motives over Q, things match up for some reason, and they don't match up for some reason. And it would be great to understand what the difference is here.
More questions? We thank the speaker.